Hello everyone, I am Himanshu Mishra and I am the PhD research scholar in the Department of Applied Mechanics, IIT Madras. So today I am going to discuss questions related to the internal flows where we will solve some problems, heat transfer problems in the internal flows. Last week we have discussed about the flow past the flat surface and the heat, how the heat transfer occurs flow past the flat surface. So we actually found the heat transfer coefficient in various types of flows like a laminar flow, mixed flow, and a turbulent flow. So in this lecture, we will be solving questions related to the internal flows. We will look some question related to the mean velocity and the mean temperature profile. And then we will look some question related to the fully developed flows as well as entry region flow where the flow is not a fully developed and there is a variation of velocity, temperature, heat transfer coefficient, pressure in the direction of the flow. So let's start with the first question here. So the first question is the velocity and temperature profile for the laminar flow in a tube of radius R0 10 mm have the form and determine the corresponding value of mean temperature and the velocity at this axial position. So we have a tube given in the question. And there is a flow. So this is my radial direction. This is my R0. And the temperature and velocity is actually changing in the radial direction, not in the flow propagation direction. So we have given the velocity and the temperature profile, and we need to find the mean value of velocity and temperature. So velocity is given as whereas the temperature is given as so to find the mean velocity, we will have an expression. So this is the expression for finding the average velocity. So we need to put the profile of the velocity here, and we need to integrate this over the value of r from 0 to r. Now we can non-dimensionalize this equation with R0. So we can also write the above equation in like, so here I am multiplying and dividing the equation with R0 square. So I will get here. So earlier my equation was dimensional, so I was integrating with respect to r. Now I am integrating with respect to R by R naught, which is some non-dimensional parameter here. So earlier I am integrating with from 0 to R, but now I will integrate from 0 to 1 because this R by R naught quantity will be vary from 0 to 1 only. So now let's integrate this quantity with respect to R by R naught from 0 to 1. We will get so I integrated this term here, and when I put the value of upper limit and the lower limit inside this expression, I will get main velocity as 0.0 meter 0.05 meter per second. Now similarly we can use the mean temperature relation to find the average temperature. So we know that how to find the mean bulk temperature. So here we need to substitute the expression of velocity and the temperature in this, and then we need to integrate the following. So we will be doing the same thing. We will non-dimensionalize this length scale, which is R in our problem with R naught. So we can integrate with respect to 1 to 0, and we will integrate by this R by R naught, and this will be my product of velocity and temperature, which is a function of R by R naught, not just R but R by R naught here. So we already find the mean velocity, which is 0.05. So I'm just directly putting the value. Again, I will multiply and divide the expression with R naught square. And since my expression become non-dimensional, I will integrate. The upper limit will change. So basically it is 0 to 1 now. So here I am integrating with respect to R by R naught. So this is my full expression. So this is my velocity profile given in the question, and this is my temperature profile. And I am integrating this from 0 to 1. So by performing the integration, by simplifying the equation, we will get something from solving this. The mean temperature will be 367 Kelvin. So this was a simple problem. So we have given the velocity and the temperature profile, and we just need to find the average velocity and the temperature. For this, we actually take the average of velocity and temperature. We non-dimensionalize the equation with respect to R naught. So we multiply and divide the expression with R naught square, and then we integrate the expression with respect to R by R naught. We change the upper limit accordingly, like from 0 to 1, and then we find the average velocity and the temperature. So next, move to the different question number 2. So in this question, in a particular application involving fluid flow at a rate m dot through a circular tube of length L and diameter d, the surface heat flux is known to have a sinusoidal variation with x, which is given here. The maximum flux is known constant, and the fluid enters the tube at known temperature Tmi. Assuming the convection coefficient to be constant, how do the mean temperature of the fluid and the surface temperature vary with x? So we need to find the temperature of the surface as well as the mean temperature. Basically, what is how the mean temperature and the surface temperature are related to x or are dependent on x. So we have given the heat flux, which is sinusoidal in nature in the question. So there is a tube. So temperature of the inlet. So this is my inlet. This is my outlet. So the temperature at inlet be, let's say this, and at outlet, let this is my temperature. So the temperature at the surface is Tx, and there is the heat flux at the surface of the tube, and the heat flux is defined as this is my given expression of the heat flux in the question. So I need to define the mean temperature and the surface temperature. So let's find first the mean temperature. So we need know the heat transfer relation. So if we have given the inlet and outlet temperature Tmi and Tmo. So like if we have the inlet temperature and the outlet temperature, and this temperature are not equal to each other, that means there will be the heat transfer along the flow propagation, along the flow direction. So in that case, the heat transfer will be given as So here I am taking the small element area and I am trying to calculate the heat transfer rate along the flow propagation direction. So this will be my expression for the heat transfer. So here P is the parameter and Q double dash is the heat flux. So we have already given the expression for Q dash in the question. Here M is the mass and C is the heat capacity. So I can rearrange this equation. So now we need to put the expression of heat flux into this expression. And my parameter will be just pi d for the tube. So now I need to integrate this expression to find the average temperature or the TM. So I will be integrating this expression, and my upper limit is the outlet temperature, and the lower limit is my inlet temperature. So as I said that I have considered a small element having the length of dx. So I will be integrating from 0 to x at the right hand side. So on integrating, I will get so here this variable q double dash sm is a constant, so I can take this out of my integral expression. So the only quantity will be inside is sine pi x by l, and I need to integrate this over a range of 0 to x. So after integration, it becomes cos pi x by l, the limit of x to 0. So the mean temperature will be then I will write this in a positive quantity. I will take here the minus sign inside the bracket. So this is my average temperature. So my average temperature is a function of x, and it is actually periodically vary with x. So to find the surface temperature, we can use the relation that we have introduced early in the question. So initially we actually define here basically I'm using the Newton's law of cooling. find the surface temperature. So I can put the given expression of heat flux here. So this will be my temperature of the, expression for the surface temperature. I can further put the value of mean temperature here, since we already calculate the mean temperature, which is a periodic function of x in equation 1. So we can substitute this equation 1 into the surface temperature equation here. So my first part will be the function of the heat transfer coefficient that we will get from the Newton's law of cooling. And the second part that we have find in the mean temperature profile is the function of the heat flux and the heat capacity rate. So now this is my overall expression for the surface temperature. So I have a tube here. So we have given the inlet temperature and the outlet temperature, and we calculate the heat transfer rate in the flow direction to the equation number A, and there will be heat transfer from the surface as well, since the temperature at the surface Ts is greater than the mean temperature. So there will be the heat transfer from the surface to the mean temperature, which is defined by the Newton's law of cooling. So by using the equation N and equation 1, we will get the mean temperature profile as well as the surface temperature profile. So let's move to the next question. So a device that recovers the heat from the high temperature combustion products involves passing the combustion gas between parallel plates, each of which is maintained at 350 Kelvin by water flow on the opposite surface. The plate separation is 40 mm. And the gas flow is fully developed. The gas may be assumed to have the properties of atmospheric air, and its mean temperature and velocity are 1000 Kelvin and 16 meter per second. So we need to find the heat flux at the plate surface. And in the second part, let's say we introduce the third plate in between the two plates, which is 20 mm thick, is suspended midway between the original plates. So in that case also we need to find the heat flux. So let's consider the first case. So in the first case, we have a channel and we have given the H. The surface temperature is 350 Kelvin. And there is a flow from the left. The mean velocity and the mean temperature is given. And we need to find the heat flux. So to find the heat flux, we will use the Newton's law of cooling, and we need the heat transfer coefficient for that. And for the heat transfer coefficient, we will use the Nusselt number correlation. So we need to identify whether the flow is in laminar or turbulent. Accordingly, we will use the Nusselt number correlation to find the heat transfer coefficient. So since we have a channel flow, we will first find the hydraulic diameter, which is given by the ratio of the cross surface area and the parameter. So h is my height and w is my weight. So we will get the hydraulic diameter as 80 mm. We will find the Reynolds number to identify whether the flow is in laminar or in turbulent regime. So we will be using the mean velocity and the hydraulic diameter in the Reynolds number expression. So the density would be 0.348. And this is the hydraulic diameter we already found. And the viscosity will be 424.4 10 to the power minus 7 in kg per second meter. So the Reynolds number would be around 39,000. So definitely the flow is in turbulent flow. So now we will be using the Nusselt number correlation for the turbulent flow profile. And we will get the Prandtl number from the properties of the flow, which is which is 0.76 for the gas, usually 0.76 for the gaseous flow. So on solving this, we will get the Nusselt number close to 100. And we know that the Nusselt number can be written in terms of the heat transfer coefficient. So the Nusselt number is actually the non-dimensional heat transfer coefficient. So I can write as, so this is my hydraulic diameter actually. So I'm just putting the value here. So this is my hydraulic diameter and this is my Nusselt number that we just found. And my heat transfer coefficient would be around 82.6 watt per meter square Kelvin. Now we have a heat transfer coefficient, so we can find the heat flux from the Newton's law of cooling. So we have given the surface temperature as 1000 Kelvin and the mean temperature is 1000 Kelvin and the surface temperature is 350 Kelvin. So the heat flux is 3.7 kilowatt per meter square. So we get the heat flux for the case A where there is a flow flowing in the channel. We first found the hydraulic diameter and the Reynolds number to identify whether the flow is in laminar or in turbulent regime. Then we identified the Nusselt number correlation for the turbulent flow and we found the heat transfer coefficient. And once we got the heat transfer coefficient, it is easy to find the heat flux. So let's move to the case B. In the case B, we will have a third plate of 20 mm thickness. So this is my third plate which I placed between the my initially first and second plate, and now my flow is hindered. So there is a flow at the top and the bottom of the third plate. Now to get the velocity in the top of the third plate as well as the bottom of the third plate, we will use the continuity equation. So I can write my continuity equation as this is my mass flow rate for the case A, and this is for case B with additional third plate. So we need to find this average velocity. So I'm just putting the values. Can get. So velocity for the case B would be given as 120 meter per second. So this was my area 40 mm for the case A, and when we introduce the 20 mm thick plate, my cross sectional area get reduced by half. So accordingly my velocity will be doubled from the earlier case from the continuity equation. So we get the velocity 120 meter per second in this case. Now we will be using a similar analysis that we have done for the case A. We will find the Nusselt number, heat transfer coefficient, and then the heat flux. So the Reynolds number would be around 20K. That means for the case B as well, we have a turbulent flow. So we will be using the same Nusselt number correlation. So I'm just putting the value of Reynolds number, Prandtl number. We will get Nusselt number is 56.9. The heat transfer coefficient will be around 190 watt per meters per Kelvin. So now we just using the Newton's law of cooling. We already know the mean temperature and the surface temperature. So this will be my heat flux. So in this question, we found the Reynolds number to identify the flow pattern, and then we find the Nusselt number. From there we got the heat transfer coefficient, and then it is easy to find the heat flux from the after we found the heat transfer coefficient. So we found that if we introduce the plate between at the middle of the channel, the heat flux actually increases, and the heat transfer coefficient is also increases, and it actually gets double from when we compare to the case A. So let's move to the next question. So the next question we have electronic circuit board dissipating 50 watt in a sandwich between two ducted force air cooled heat sinks. The sinks are 150 in length and have 24 rectangular passages, 6 by 25 The atmospheric air at volumetric flow rate of 0.06 meter cube per second and given at a temperature of 27 degrees Celsius. We need to estimate the operating temperature of the board and the pressure drop across the sink. So we have given a IC circuit and the inlet temperature is given as 27 degrees Celsius and we have given the volumetric flow rate 0.06 meter cube per second. The size of each IC circuit is given as 6 by 25 So the air outlet temperature, we can find the air outlet temperature from which is the mass flow rate So if I consider the density of air, let's say 1.12 kg per meter cube, so I will get the mass flow rate of 6.77 10 to the power minus 2 kg per second. So we have given the inlet temperature. So we have already discussed in the first question that if we have an inlet temperature TMI and the outlet temperature is TMO, then we can define the heat transfer along the flow direction as now we need to find the temperature at the outlet, so we need the information about the heat transfer which we have already given in the temperature. So I can write so my heat transfer is 50 watts. This would be this will be by temperature at the outlet. So we just need to put the value here. So we already calculate the mass flow rate, which is 6.77. my heat capacity rate would be around 1000. And this is the temperature at the inlet. So on calculating, we will get the temperature of the outlet is around 27.73 degrees Celsius. Now we need to find the operating temperature of the IC circuit. For that, we need to calculate the surface temperature. So to calculate the surface temperature, we will be using this question number 1, let's say. And to calculate the surface temperature, TS, we need to find the heat transfer coefficient rate. So again, we will be using the Nusselt number correlation. And for that, we first need to check whether the flow is in laminar or in turbulent state. So for that, we will finding the Reynolds number. So first, find the hydraulic diameter. So I'm writing all the dimension in millimeter. So my hydraulic diameter would be around 9.68 millimeter. And I can find my average velocity. Which is 16.7 meter per second. So number would be around 10,000. So which says that my flow is in turbulent region. So we have a turbulent flow. That means the Nusselt number for turbulent flow will be having a dependency of Reynolds number to the power 4 by 5. So I'm putting the value of Reynolds number in the Prandtl number. So I will get Nusselt number of around 30.6. And we can directly get the heat transfer coefficient from the Nusselt number expression. This is my hydraulic diameter. So my heat transfer coefficient is 85.4 watt per meter square Kelvin. Now we can find the surface temperature. So we already find the outlet temperature and we have already given the inlet temperature. And we found the heat transfer coefficient. We found the mass flow rate, and rest of the variables are just the properties of the fluid. So this is my outlet temperature, and this will be my inlet temperature. Again, I am writing the length dimension in millimeter. So this is my parameter in millimeter. And this is my heat transfer coefficient. So I require the mass flow rate as well as the heat capacity. We already found the mass flow rate 6.77 10 to the power minus 2. Now on solving this expression, we can find the surface temperature is 30 degrees Celsius. So in this question, uh, we first found the mass flow rate, and since we have given the inlet temperature, we use the equation 1 to find the outlet temperature. We have also given the total dissipation rate from the IC chip. So then to find the mean temperature, we use the constant temperature relation, which is given in equation 1. And for that, we require the heat transfer coefficient. So to find that, we use the turbulent Nusselt number correlation to find the surface temperature. So let's move to the next question. Let's move to this 8th question. So it says that the engine oil is heated by flowing the fluid through the circular tube of diameter 50 mm and length is 25 meter, and the surface is maintained in 150 degrees Celsius. So if we have given the flow rate 0.5 kg per second and the inlet temperature of 20 degrees Celsius, we need to find the outlet temperature and the heat transfer rate Q. So in this question, we need to first identify whether the flow is in fully developed flow or it is in the entry region. So for that, we will use the correlation where the entry region length is a function of Reynolds number and the Prandtl number. So let's X is my entry length of the entry region. And I will use this correlation here. So we need to find the Reynolds number first. Since we have given the mass flow rate 0.5 kg per second, I will write my Reynolds number expression in terms of mass flow rate. So just putting the value here. So 0.032 is my viscosity. So the Reynolds number will be 398. And I can get the Prandtl number from the properties of the fluid. So the entry length region is 486 meters, and we have given the length of the tube 25 meters, so which is way shorter than the entry length region. That means the flow is not a fully developed flow. So in order to find the heat transfer coefficient and the total heat rate, we need to use the Nusselt number correlation that is valid only for the entry region, not for the fully developed flow. So in the earlier question, we used the Nusselt number correlation for the turbulent, fully developed turbulent and laminar flows. Here the Nusselt number correlation will be different, and it is given as we already know the Reynolds number and the Prandtl number. So we just need to put the values, and we will get the Nusselt number of 11.95, and we can get the heat transfer coefficient directly from the Nusselt number. So 0.13 is my heat thermal conductivity, and 0.05 is my diameter. So my heat transfer coefficient would be 33 watt per meters per Kelvin. To find the mean temperature or the outlet temperature, we will use the expression that we already used in the previous question. So we have given the inlet temperature. So this pi d is my parameter. So in the previous question, I have written directly P. Now I am writing pi d, which is the parameter for the tube. So we have already given the surface temperature and the inlet temperature, and we just need to find the outlet temperature. So it is quite similar to the previous question where we need to find the surface temperature. So for that, we actually first found the outlet temperature, and then we begin by finding the surface temperature using the same relation. Here we have given the inlet temperature only and the surface temperature. So just putting the value in this expression, we will get this quantity is inside the bracket. Just putting the values, I will get the temperature at the outlet is 35 degrees Celsius. So now we have the temperature at the outlet of the pipe, and we already know the inlet temperature. So we can find the heat transfer. There is a variation of temperature at inlet and outlet, so the heat transfer can be given by mCp delta T. So my heat capacity would be around 2000, and I am writing the temperature in degrees Celsius. So I will get my heat transfer at around 16 watt. We solve this expression. So in this question, we first identify whether the flow is in the fully developed region or the entry length region, and we found out that the flow is still not fully developed. So we use the Nusselt number correlation, which is valid for that particular region. We found the heat transfer coefficient, and from the constant temperature relation, since we already have given the surface and the inlet temperature, we found out the outlet temperature, and then from the mCp delta T relation, we got the heat transfer rate. So let's move to the true and false question. So here we need to identify whether the statements are correct or not. So the first statement is, during the laminar flow, the magnitude of Prandtl number is the measure of relative growth of the velocity and thermal boundary layers. And for the gas, the Prandtl number is equivalent to 1. That means the two boundary layers coincide with each other. So we actually already discussed this question in the week 4, where we actually compare the thermal and hydrodynamic boundary layer based on the value of the Prandtl number. So yeah, the statement is correct. So for the gaseous flow, the Prandtl number is equivalent to unity. That means my thermal and hydrodynamic boundary layer will coincide with each other. So my first statement is correct. The second statement is says that for the fluid with Prandtl number greater than 1, such as oil, the velocity boundary layer outgrows the thermal boundary layer. As a result, the hydrodynamic entry length is smaller than the thermal entry length. The opposite is true for the fluids for the Prandtl number less than 1. So let's say I have a channel. So X is my length of the entry length. So this is my entry length and this is my fully developed region. So if my hydrodynamic boundary layer is higher, that means it will quickly become fully developed length. Let's say the entry length for this case is x1, and if my for the less Prandtl number value, my hydrodynamic boundary layer will be developing, and for this the entry length would be x2, and we can here clearly see that x1 is smaller than x2. That means for the higher value of the Prandtl number, the hydrodynamic boundary layer will quickly develop within shorter span of the shorter length of the channel compared to when my Prandtl number is of the lower magnitude. So my second statement is also correct. So the option here is, so the correct option is A. This is true. So let's conclude this class. So in this, for the today's class, we actually solved the problem of mean and finding the mean velocity and the temperature profile, and then we went up to solving the heat transfer which are related to the internal flows. We first solved the fully developed flow where we found out that Nusselt number. We first identify whether the flow is in laminar or in turbulent regime. And then we actually identify the Nusselt number correlation according to that, and then we found the heat transfer rate. We also looked one question related to the entry length region. That means the flow is not fully developed to the entire length we have given, and we actually found out the heat transfer rate in that region. So for the next week, I will solve the remaining portion for the internal heat transfer flow, and we will also look some question related to the boiling and evaporation problems.